Newton 2. Here we have one trolley from our previous video. Here we have another trolley hanging over a pulley. We've set this mark on the 0. We're going to let this go and we're going to watch the acceleration that ensues. On our marks, get set, go. Now on iMovie, I've advanced the video to where we're about to let go of the trolley that's pulling the trolley that's moving horizontally. So we're about to start the problem, and I'm going to advance. Each frame is 1/30th of a second. I'm going to advance it, and I'm going to record the values that we note. So we're going to be looking at here. There it starts at 0. And if we advance it one frame, it looks at about 0,5. Next frame, it looks like 1.5. There's 1, 1.5. And so on. 2,8, 4, 6, 7,5, 9, 11, 14, 17, 20, 24, and finally it ends up here at about 27. I'm taking it where the faintest front mark is. Obviously, as it's moving, it's getting more and more blurry. So now we've got our measurements. Let's go to a spreadsheet and put those displacements into the spreadsheet. Here we've created a spreadsheet on docs.google.com/spreadsheets. Here you will recognize were our values which we read, but they've been converted to meters. So this was the X values, or the position of the trolley. Then here was this one minus that one. So it gave us the difference between this and that displacement. Then we divided it by we divided this value by, we multiplied it by 30 to get a velocity. It's actually dividing it by 1/30th, but that means multiplying it by 30. So here's the velocity between this time and that time. Then here we've got the difference between that and that. 0.39 and 3 is 0.09. And then in this column, it works out the acceleration, which is that difference, the delta x value divided by 1/30th or multiplied by 30. So here is our acceleration. I've just moved this down a little bit, and there we can see the average acceleration, 2,25, and that would be meters per second squared. So there's the average of all those first few accelerations, and there it's averaged out at 2,25. I hope you're enjoying our little experiment, and I hope you're enjoying physics being fun with me, Stephen Thomas. Now, that little experiment falls under the category of Newton's laws, and usually they involve something there on a desk, and maybe a weight hanging from, and there's a pulley and they're attached by a string. Or it could be a truck pulling a caravan or something. There's normally A with a tow rope or a string pulling B. Now, you may say, but I don't find this series on revolutionary science teaching revolutionary. You're just doing what everybody else does. Well, let's ask if that's true or not. That little experiment, would most teachers get their learners to pull out their smartphones? Do they even allow their smartphones in class? I encourage them. Perform a little experiment whereby we've got 2 trucks and a piece of string, and then they film this one truck falling over the edge, pulling another truck. Namely what we did here. I don't think so, because they're too busy giving notes. So there's second point. First point is I do experiments, and I want the kids to do them. Second point, I'm not a believer in notes. I want it up here. So if I was teaching, and when I teach Newton's laws, Newton's got 3 laws, and this is how we teach it. First of all, we say it's a vector. second of all, we say, therefore it's got a direction positive. So some direction, let's say in this case, everything moves that way and down. We're going to say the direction of movement is positive. I get the kids to act out that and that, positive, the direction of movement. Then we will not give them, they need to know Newton's first law. Now here's how we do it. We say there's Newton's first law. And we get them to act it out. So an object that's at rest will remain at rest unless acted upon by an unbalanced force. Or an object that's moving will carry on moving at a constant velocity in a straight line unless acted upon by a net force. So now by them doing this or that, so we use this to represent Newton's first law, that things just keep on doing what they're doing, keep on moving in a straight line. That's the natural order of things. Then Newton's second law we represent like this. So something accelerates. And so if I ask them which law it is, the whole class does. That means it's its second law. Third law is where for every action, there's an equal and opposite reaction. For every force, say to the right, there's an equal and opposite force to the left. So this is how they represent, say, Newton's third law. So if I ask them, what's Newton's first law? I want them to do this. Or just that, that's also the same. If I say, what's his second law? I want them to show acceleration. If it's the third law, I want them to show, now there's two objects involved in the third law, action, reaction, two forces involved. In Newton 1 and 2, there's only one object and one force involved. And in fact, Newton 1 is just a variation of Newton 2. So let's have a look at Newton's second law, which is here. Force equals ma. Now that's the only formula that they have in this section to work with. And if they were asked to put it in words, they will say a force causes a mass to accelerate. The greater the force, the greater the acceleration, the greater the mass, the less the acceleration. So that is the second law. But the first law, which is a special case, it's when there's no net force, there's no net acceleration. So how do we represent no net acceleration? There is no net acceleration, or standing still is no net acceleration. So Newton's first law is just a special case of his second law. So there's not much to the section. There's actually not much to memorize. And then normally we'll grab a paper and start working from those questions right from the beginning. That's revolutionary science teaching. So I'm not giving a lot of notes. And if we're doing, say, the problems from the paper, we'll grab a past paper, say it looks something like this, and they normally ask you to calculate the acceleration, and then you will tell them there's basically two ways you do this. You apply Newton's second law to everything, so to the whole system. So you say, what is the net force? Well, the only thing that's pulling this whole system is this weight. So you take that mass, you turn it into a force downwards, a weight, and that would be your net force. If you just lift it up, that stays exactly where it is. So that's not contributing any force. It's only this one's weight, which is the net force. And then it causes both masses to accelerate. So you have to add that mass, 0.35, to that mass, 0.187, to get your masses. And then you substitute and you work out your acceleration. So now that's revolutionary. We're telling the kids, go home and do it yourself. But we can work out the acceleration. We know you can change the subject or the formula. And then, if necessary, we go one further and we say, now we apply Newton to just say B, string B. So, getting a piece of chalk, you may be asked to draw a free body diagram for B. So here you've got the force of weight down, and you've got the force of tension in the string up. So there's your free body diagram. And so if you're now going to apply it to just B, suppose we know the acceleration is 2.25, we now apply that to just B alone. What is the net force on B alone? Well, it's that force and that force. You add the two together, you get net force. What's the mass of B alone? 0.187. And we know the acceleration of B because we've observed it was 2.25. So now we can find what this one plus that one's net force is. net force, and so now we can calculate the net force or the force of tension, since we already know how to calculate and turn 1,87 kilograms into a weight by multiplying it by 9,8. And again, that is also a special case of Newton's second law, because to turn mass into a weight, we say force equals mg. And the mass here is 0,187 times 9,8. That's the acceleration due to gravity. So it's a special case of Newton 2. So this formula is a special case, and we use this formula to calculate the weight. And then the net force, when we add those two, we'll be able to calculate the tension in the string. Then we can go and apply Newton 2 to just A, because the tension in the string, if B pulls on A pulls on B. Case of Newton 3. So we have Newton 3 in operation here because B pulls on A, the tension in the string is the same as A pulls on B. So once we've calculated the tension in the string, we know the force here. And if there was friction to the left, we could again apply a similar thing. We could have a free body diagram, force of friction and force of tension. That tension would be the same as that in that direction, and then we could calculate the frictional force using again this net force, add those two, equals that mass times that acceleration, which is 2,25. Now if I'm holding my hand on there at the start of the problem, we ask them, is it moving? No. So what is it a case of? Newton? Is it this? Is it this? Or is it this? So it's Newton 1. The forces must be balanced. So when I'm holding it and it's stationary, all the forces are balanced. So if it's balanced, what do we know about this force and that force in the case of B when we've got our finger on it? Well, that must be equal to that for B not to be moving. Newton 1. The net force must be 0 for no acceleration, and so on. So we discuss the problem, and we go through many different past exam papers, just saying, how would you solve this problem? If I had to ask you the tension in the string, how would you do it? So, what is revolutionary about it? Well, we're doing experiments. We're acting out the problem. So by us acting this whole thing out, they're learning. And then we've told them, first solve it for everything, then draw your free body diagram and solve it for each individual weight or mass or trolley that's being accelerated. And then you will find whichever force you are looking for.